We're going to dive into the concept of prime factorization, which is a pretty big idea when we work with numbers and just arithmetic and operations and things like that, because any number that is not prime is composite, and all composite numbers can be written as a product of primes. So primes end up being like the building block for all numbers. So we're getting a little ahead of ourselves. Let's define a couple things first. So first off, a prime number is a natural number with exactly two different factors, itself and 1. Now when I say it's a natural number, the natural numbers are sometimes also called the counting numbers. So the counting numbers would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Right? That set of numbers is called the counting numbers. All right, so if you are a counting number and you've got exactly two different factors, 1 and itself, you are considered to be prime. Otherwise, if you are not prime, you are a composite. So sometimes a composite number is defined as being a number that is not prime. Or we could define it as it's a natural number that has more than two different factors. Now, in our number system, 1 is called the unit. Right? So the unit is neither a prime nor a composite. Some definitions of prime allow 1 to be prime, but the definition that we are working with will not allow 1 to be prime. So 1 is not prime, 1 is not composite, 1 is called the unit. All right, so it's helpful to be able to recognize the prime numbers that are less than 100. All right, so right here I have a table of the numbers from 1 to 100 grouped in sets of 10. So the first row is 1 through 10, the second row is 11 through 20, and so on. So let's go through this table and identify all the prime numbers that are less than 100. So remember that 1 is not prime and 1 is not composite, so I'm going to put an X through it. So 2 is prime. 2 is actually the only even prime. All right, so any other even number has more than two factors. So for instance, 4 as a composite number. The factors 4, or the things that divide 4 evenly with no remainder, are 1, 4, and 2. Right? So 4, like for instance, would not be considered prime, and actually all even numbers. So anything that ends with a 2, 4, 6, 8, or 0, those are all composite numbers that we could then find what's called their prime factorization. So running through here, I'm just going to go ahead and X out all those evens because 2 is kind of special. 2 is the only even prime. Okay, so 3 is prime, 5 is prime, 7 is prime, 9 is not prime because the factors that divide 9 are 1, 9, and 3. 11 is prime, 13 is prime, 15 is not prime, 15 is composite, 17 is prime, 19 is prime. Moving into the 20s, 23 is prime, 29 is prime. 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. Those are all the primes that are less than 100. Any other number has more than the two factors, itself and 1. And if you are unsure about any of the other ones that I didn't circle, I encourage you to sit there and try to figure out what other things divide it other than 1 in that number. Okay, so every composite number can be written as the product of prime numbers, called its prime factorization. So remember that when I say product, this means we're going to multiply a bunch of stuff. So, and then the only things I'm allowed to multiply are prime numbers themselves. So this is kind of a cool fact. It's actually so important. It's called the fundamental theorem of arithmetic. All right, so fundamental theorem in mathematics usually means big idea. All right, so any number that is not prime can be written as multiplying a bunch of primes together. So when we go through this, a couple of things to remember. Remember, 1 is neither prime nor composite, and every number has 1 as a factor. So 1 divides everybody, and the number itself will divide the number. The question is there anybody else? Every natural number greater than 1 must fall into a category of either being prime or composite. All right, so let's show how to find these prime factorizations. So the example that I like to always do is 24, because there's a lot of ways to break down a 24. So a couple ways to find this guy's prime factorization. There's kind of 2 major methods I've seen. One of them is called a factor tree, and another one is called short division. I've also seen this called the birthday cake method, depending on how you record your division. All right, so I'll show you both techniques. All right, so for the factor tree, what you're going to do is you're going to put the number at the top, and you're going to draw 2 branches for what 2 things must I multiply together to get to 24. Now, 1 times the number is not going to be under consideration, because that works for all numbers. The question is there anybody else? So at this point in time, you don't even have to worry about primes. You're just thinking, what 2 numbers multiply together to give me 24? The first set that comes to your mind, write it down. So maybe you were thinking 4 times 6. All right, cool. So we'll just put those at the end of the branches. So 4 goes at the end of one branch, 6 at the end of the other branch, and it doesn't matter if it's bigger or smaller, just put them at the end of the branches. Now, at the end of a branch, if the number isn't in itself prime, you would stop. If it's composite, you keep going. So 4 is composite. There's another way to get 4 other than 1 times 4, specifically 2 times 2. So I'm going to draw 2 lines from the 4, and at the ends of those lines, or those branches, I'm going to write 2's. Now 2 is prime, so I'm going to stop. Sometimes to remind yourself to stop, once you hit a prime, it's helpful to circle the numbers to remind yourself we don't go any further. Now I come over here to this other branch, the 6. Is there any way to get a 6 other than 1 times 6? Yeah, 2 times 3. So I'm going to draw 2 lines, and I'm going to put 2 at the end of one branch, 3 at the end of the other branch. 2 is prime, 3 is prime, so I'm done. I've got prime numbers at the end of all my branches, so the prime factorization of 24 is 2 times 2 times 2 times 3. Or if you want to get really fancy, you can write this with exponents. So the 2 times 2 times 2, I can write that as 2 to the 3rd power times 3. Now you might be like, but wait, I wasn't thinking about breaking down 24 like that. That's okay. All right, so let me show you maybe a different way to do this. So 24, maybe you were thinking about 24 as being 2 times 12. Well, 2 is prime, so I would stop on that branch. 12 is composite, so I can keep going. 2 numbers that multiply to 12? Well, maybe you were thinking 4 times 3. So I'll put those at the end of the branches. 4 is composite, so I can keep going. 4 can break down into 2 times 2, where 2 is prime, so I stop at the end of both of those branches. Now the 3 was prime, so I'm done at the end of that branch, and so I'm done. I've expanded out all my branches, so then my prime factorization, again, is 2 times 2 times 2 times 3. So you'll always get the prime factorization because it is unique to the number. It doesn't matter how you break down the numbers along the way, as long as you're using your multiplication facts. All right, pretty cool, huh? So you and somebody else could break down the number differently along the way, but we'll all get the same prime factorization. Now let me show you this other method called the short division, which is also sometimes called the birthday cake method. So I'm going to do 24, and for the division you can either divide down or divide up, depending on the space on your paper and how you want to record your work. If you do the division upwards, that's where the birthday cake kind of comes into play. So I would ask myself, for 24, what prime divides 24? And this is where it's helpful to maybe know some divisibility rules for 2, 3, and 5, which are the first 3 primes. If you wanted to test if it's divisible by 7 or 11, this is where maybe you're just more helpful to pull out a calculator. So 24 is divisible by 2, so I'm going to divide it by 2. So I'm going to put 2 on the outside, and 24 divided by 2 is 12. So I'm going to write 12 up here on the top. Now I'm going to stay with the prime of 2 until I can't use it anymore. So 2 still goes into 12, so I'm going to write another divided by symbol and put 2 on the outside. 12 divided by 2 is 6. Again, I'm going to keep dividing by 2 until the number I have isn't even anymore. So 6 is even, so I can divide it by 2 again. 6 divided by 2 is 3, and 3 is prime. So once you hit a prime on the top, you're done, and then you're going to grab all the numbers along the side as well. So 24's prime factorization is again 2 times 2 times 2 times 3, or 2 cubed times 3. All right, you could also do the division going downward, meaning I'll show you really quick. 24 divided by 2, you could record the 12 right here, and you could go downward with the division if you would rather do it like that. All right, very cool. So let's do a couple more examples. Let's find some prime factorizations. I would encourage you, if you're comfortable, to maybe pause this and try these 3 problems on your own. If you want to see a couple more examples before you try one on your own, that works as well. So the 3 examples we're going to work through is 546, 212, and 5,759. We are going to find its prime factorization. Now, just as a heads up, when you're doing prime factorization, it's really helpful to have a calculator with you as opposed to trying to do these divisions by hand. The idea is we're trying to break these numbers down into these prime building blocks, and we kind of want to do it rather quickly because we usually use this as a stepping stone for maybe like another skill or another math technique. So we want to be able to get this prime factorization quickly so we can do some stuff with it. So for 546, I'll show you the factor tree method again. So 546, I'm going to draw 2 lines underneath it, and I'm seeing that this number is even, so sometimes it helps to not overthink it. 546 divided by 2 is 273. So I'll put 2 at the end of one branch, 273 at the end of the other branch. 2 is prime, so I'm done over there. I'll keep working on the 273. Now 273 is not even, so another 2 is not going to work. But now I'll check for if it's divisible by 3. The sum of the digits, 2 plus 7 plus 3 is 12, and 12 is divisible by 3. So this number is divisible by 3. So using your calculator, 273 divided by 3 is 91. Right, so the 3 is prime. I'm done on that branch. 91 is not prime. So we will break down 91. 91 is divisible by 7, specifically 7 times 13, where 7 is prime and 13 is prime. So I would be done. I've got prime numbers at the end of all my branches, so the prime factorization for 546 is 2 times 3 times 7 times 13. Now the order in which you write your primes doesn't matter, but we tend to write them from smallest to biggest just to kind of have some consistency. But as an example, if you were to write like 13 times 2 times 7 times 3, that would be fine as well. I'm just looking for you that you have the numbers in your list and that you're multiplying them, the order, and whether or not you're using exponential notation, if applicable, doesn't really matter at the end of the day. All right, let's try the next one, 212. And then for this one, I will show maybe the birthday cake method again, or that short stack division. So 212, we want to start with the first prime, which is 2, and we're going to ask ourselves, does 2 go into 212? And it does. So 2 goes into 212 106 times. So we'll write 106 above the line. Now 106 is still even, so I can still divide this by 2. 2 goes into 106 53 times. We'll write 53 above the line. And 53 is prime. So this is why it's helpful to be able to recognize primes that are less than 100, because it lets you know when you need to stop. So we'll grab the numbers along the outside and the number at the top of our cake. So 212's prime factorization is 2 times 2 times 53, or you could write that as 2 squared times 53. All right, very cool. So let's try this last one. So 5,759. So 5759. So first off, it doesn't end in an even number, so this isn't divisible by 2. And if I add the digits, 5 plus 7 plus 5 plus 9, I would get what is that, 10 plus 16 or 26, and 3 does not go into 26 evenly with no remainder. So this number is not divisible by 3. It's not divisible by 5 because it doesn't end in a 5 or 0. So my first few primes are out. So then I would use my calculator to check, is 5759 divisible by 7? And it's not. Is 5759 divided by, let's see, the next prime after 7 is 11, and it is not. And then 5759 divided by 13, that works. All right, so 13 and 443. All right, so let's think about what we've done so far. So I've already checked the primes of 2 against 5759, it didn't work. 3, 5, 7, and 11. So I've checked all these primes against the 5759 and none of them worked. So if they didn't work for 5759, they're also not going to work for 443, right? We're not going to have a prime embedded inside a smaller number that wasn't part of the bigger number. Now I've already looked at the prime of 13, so then at this point in time I would be checking primes bigger than 13. Now another fun fact, okay, is when you're looking at a number and you're checking for primes, you would just have to check primes that are less than the square root of that number. So for example, the square root of 443, you can use your calculator, this is approximately equal to 21. So if I'm looking for primes that divide into 43, we would have to check any prime that is less than 21, right? This is something in number theory that we can prove to be true. So if I want to see if anybody divides 443, I would just have to look at any primes that are bigger than 13 but less than 21. All right, so the primes that I would have left available to check would be, let's see, the next prime after 13 is 17, and the next prime after 17 is 19, and the next prime after that is 23, which is too big. So then for 443, I would just use my calculator to see does 17 go into it, and it does not. And for 443, I would check if 19 goes into it, and it does not. It doesn't go in evenly. So at that point in time, there is no other way to break down 443 other than 1 times that number. So 443 is prime. All right, so that's not one we would necessarily be able to recognize by sight, but this is a cool idea from number theory. So you would check the square root of the number. Okay. So for whatever number, you're going to take its square root, and for that result, you have to check any prime less than that. If the number is divisible by a prime, it would have to be less than whatever the square root value is. Right, so 443 is prime, so 5759's prime factorization is 13 times 443.